the energy levels of a system which is in equilibrium at temperature T, which is 1 by kb beta. We know beta is equal to 1 by kBt. The energy levels are 0, epsilon and 2 epsilon. If two identical bosons occupy these energy levels, the probability for the system to take the total energy as 3 epsilon is to be calculated. So we have two bosons which can be distributed in 3 energy levels. Okay. So the number of possible distributions are given by this. We have 3 energy levels, 0, epsilon, 2 epsilon. And the 6 different ways of distributing the particles are given here. Here the total energy is 0 because 2 particles are in the 0 energy level. Here the total energy is 2 epsilon since the 2 particles are in the energy level epsilon. Here the total energy is 4 epsilon because 2 particles are in this energy level. Here it is epsilon the total energy because one particle is in 0, the other particle is in epsilon. Here this is 2 epsilon, one particle in 0, other particle in 2 epsilon. Here it is 3 epsilon because one particle in 2 epsilon, one particle in epsilon. So only for this distribution the total energy is 3 epsilon. We have to find the probability for the particle to be in this state. So the formula for calculating the probability is this. Probability for a system to be in a state of energy ER is given by e to the power minus beta ER over this quantity which is the partition function sigma R e to the power minus beta ER. So we calculate the probability. So the partition function is first evaluated, which is the sum over all states of the factor e to the power minus beta ER. So it turns out to be this. So the different energies 0, 2 epsilon, 3 epsilon, 4 epsilon, epsilon. Okay. So the probability is given by this. And this is the probability we substitute in the formula. We are calculating the probability for the system to be in state of energy 3 epsilon. Okay, so that as you divide it by the partition function, you get this. So this is the probability.